So we'll move straight on now to our final presentation by Naomi Grint. Naomi joined the LoLo CDT after working in the environmental buildings industry for a number of years in a number of different roles. At UCL, she specialised in understanding hygrothermal conditions, which are the heat and water transport issues. And she's done that in solid walls before and after the retrofit of wall insulation. She now works at Etude, doing a range of things, including passive house design and the modelling and monitoring of moisture for energy retrofits. Naomi, over to you.
Thank you, Cliff. I'm just going to share my screen. Right, hello everyone, I'm Naomi. This is the title of my research, which basically means I'm studying moisture in brick walls and trying to work out what happens when you apply internal wall insulation. Why does it matter? So we need to decarbonise our built environment, and in a lot of cases internal wall insulation is the only realistic solution. One of the issues is when you internally insulate a wall, the existing structure cools down, the relative humidity rises, and there's also a limit to the amount of drying to the room that can take place. So the challenges for the industry are to work out what the risks are of this and which materials to use, how much to use and how to detail. Hygrothermal modelling goes some way to helping determine the risk, but results are significantly affected by assumptions, particularly around wind-driven rain, shelter factors and moisture transport and storage properties of the wall. So the key aspects of my research, my priority was to address the lack of data. So I've created a long-term, high-resolution in-situ data collection and a method that can hopefully be applied to other walls in the future. Today I'm going to introduce some of the uninsulated walls that some of the data that I've looked at, and also show you some plots from the insulated walls, including some preview of what's happened when moisture loads have been added and how those have dried out. So the experimental design and setup. The data set is a result of monitoring campaigns on 3 walls in 2 different buildings over 3 to 4 years, during which time 2 of the walls were insulated. A timeline at the top shows the uninsulated walls in light green and the insulated in dark green. The purple and orange indicate additional climate data and moisture content data available for walls B and C. So we have at least 1 year of data before and after insulation, and we have data from a control wall which wasn't insulated. The plan diagrams on the left explain the position of sensors through each wall. The diagram on the far left shows walls A and B uninsulated. The middle wall is wall A insulated with wood fibre board and wood fibre batt, and the one on the right is wall C, which was insulated with mineral wool behind polyurethane board. Humidity and temperature sensors were inserted diagonally into diagonally drilled holes before being carefully backfilled with brick dust, and the sensor packing process is shown in 2 of the images to the right. Additional sensors were measured conditions on the inside and outside surfaces and in the ambient environment 200 to 300 millimetres away from the surfaces. These images just show the interstitial sensors being packed behind the wood fibre board and the new sensors on the surface of the final wall build-up. This gives an overview of the data, the relative humidity data for the 4 years from November 2015 to February 2020. From the top to bottom are walls A, B and C. I know it's hard to see exactly what's going on, but I wanted to give you an overview of some of the significant parts of the data. The thick black boxes here are periods for which A and C were insulated. Wall B remained uninsulated throughout, but there are periods where the room was unheated and the windows were replaced in the middle of the plot. So the black lines in the plot show the surface and the ambient measurements. So generally high is the outside and low is the inside. The coloured lines are data from inside the wall. Blues are in the brick. Green is behind the outer brick course, and the pink and purple are interstitial behind the, between the brick and the insulation. And on wall A, there's an extra interstitial point between the two layers of insulation. So the uninsulated walls have been compared. The top row shows A and B, which were both uninsulated during 2016. Although these walls are very similar, there are slight differences in external shelter, internal occupancy and heating patterns, and potential differences in the structure, which mean there's up to a 10% difference in in-wall relative humidity at peaks during this year. On the right, relative humidity is plotted against distance using data from the 7 sensors across the 2 walls. These are measured on the same time on the same day in winter and summer for each wall. And the differences in the centre of the wall in the summer are most pronounced. In the bottom row, the data for the wall B for years 2016 to 2019 is presented, and on the plot on the right, it shows the same day in summer for the 4 years. Again, the impact of the room being unheated for winter 2017 to 2018 is notable. This slide shows some of the data from the insulated wall A alongside the control wall B, which remained uninsulated. Immediately after wall A was insulated, the outside of the wall was jet washed, which significantly increased the relative humidity in the middle of the wall, which is the turquoise blue line just there. This dropped to approximately normal levels after a year. During this time, the relative humidity at the insulation brick surface, which is shown by the purple line there, increased briefly above 80% relative humidity and did not rise above 90% at any point. And these relative humidity levels are not likely to cause a problem in these conditions. The chart on the right shows relative humidity against distance through the walls for a day in summer and a day in winter during the final year for walls A and B. In the winter, the in-brick relative humidity measurements are 10 to 20% higher in the insulated wall, increasing towards the outside surface, which can be seen here. At the brick to insulation interface, which could be seen as a sensitive junction, the relative humidity is below 70%, and it's approximately, and is approximately 50% between the 2 layers of insulation, the wood fibre board and the wood fibre bat. So this is very low. Just to summarise the findings from the results I've presented today, the moisture levels varied between the 4 years and between walls in the same building at the same orientation. And the internal wall insulation did increase the relative humidity in the existing structures as expected, but for these walls, the moisture at sensitive surfaces was not deemed problematic. It was interesting to see the response to a significant wetting event in wall A, insulated with wood fibreboard, and how the rate of drying changes at different depths through the wall. Some hygrothermal modelling results, which I haven't discussed today, showed the significant impact of some input parameters, including moisture storage and transport properties, and also showed the potential for simplification in material functions. The results I've presented are specific to the monitored walls, and they can't necessarily be applied to other conditions. However, they offer the opportunity to assess these walls in incredible detail and show how moisture is transported under various environmental loads with insulation and with a significant wetting event. More high-resolution long-term data sets would be really useful with before and after insulation and control data. Post-occupancy monitoring standards are a step towards this, and I know there's some requirement for monitoring is included in the new past 2035 document. I don't know how detailed the requirements are. From the modelling point of view, it's clear that we need to consider parameter sensitivity when modelling brick walls and other structures. We need a UK material properties database, and in the long term, in-situ parameter estimation for moisture properties of solid brick walls would be useful insight into variation across different walls in the UK. I just wanted to acknowledge the incredible support I've had from my supervisors and from my research group. I've also had loads of input from others at UCL, especially Valentina Mariccioni, and also like to acknowledge the clients, contractors, installers, architects, and everyone who's made the data collection possible. Apologies if I've overrun, but any questions can also be directed to me at the contact details shown here. Thank you very much for listening.